Okay, welcome back. We're doing topic 8.8 in the AP Calculus curriculum today, volumes with cross sections, triangles, and semicircles. We're going to calculate volumes of solids with known cross sections using definite integrals, and volumes of solids with triangular cross sections, and semicircular other geometrically defined cross sections. So we're going to start by reviewing how we calculated the area of the volume in squares and rectangles on the last one. Well, again, this will be several parts, 5-part video session for this lesson. So recall when we were reviewing or when we were calculating the area with square and rectangular cross sections, we wanted to determine the region that forms the base of the solid. Then we wanted to draw a rectangle in the region. We wanted to sketch one cross section and label its dimensions. Then we would determine an expression for the volume of one cross section. We determined limits of integration for our solid, and then we integrate the volume function to calculate the volume of the solid. So we have f of x is cosine x and g of x is sine x. We're going to determine the volume of the solid whose base is defined by the region in the first quadrant bounded by curves f of x and g of x and the y-axis, and whose cross sections are rectangular, twice as tall as they are long. So for some reason my pens are not working with my screen, so I got to draw with my fingers or the mouse, and that's a little difficult. Remember, we're going to start by sketching a curve so we can determine where this cross section is, where the base is. Remember, f of x equals cosine x. It's going to look something like that. And f of x equals sine x. Well, it's going to look something like that. Recall this intersection is going to occur at pi over 4. So now I'm going to draw one rectangle inside. Not a very good rectangle. I'm using my mouse there. Pretend that's a rectangle. Remember, the width is dx, and this one, the height of the rectangle or the length of the rectangle is going to be f of x minus g of x. So now I'm going to draw one cross section outside. I'm going to take that rectangle. This is that rectangle. Its width is dx. Its length is f of x minus g of x. And recall it's twice as tall as it is long. So its height is 2 times f of x minus g of x. The volume of one of those cross sections is the length times width times height. So in this case, that's going to be 2 times f of x minus g of x times f of x minus g of x. So I can write that as f of x minus g of x squared times dx. Now, because the region I'm in is from 0 to pi over 4 where that intersection is, I'm going to integrate that function for v, from 0 to pi over 4, the 2 times f of x minus g of x squared times dx. A lot of times on FRQs, you'll only have to set up the integral, and as long as you have defined f of x and g of x, and you can write it just like this. In my calculator, though, if I had to enter my calculator to evaluate it, I'm going to enter the integral in my calculator. I'm going to enter f of x is y1 and f of g of x is y2, but I'm not going to use the y1, y2 on the FRQ answers thing unless I've defined y1 and y2 as that. So if I was going to enter this in a calculator, what I would be entering is 2 times the integral from 0 to pi over 4. And this one, recall, it'll open with a set of parentheses, but you need to put another set of parentheses if you're going to square it. y1 minus y2, this is what I'm going to enter in the calculator, squared. And it's going to close parentheses. It's going to ask you for the variable of integration. We're going to put x. I'm going to enter that in my calculator. Remember, math 9 gets you to the integral. 0 to power of 4 is my limits of integration. Inside, don't forget that inside set of parentheses to insert that. So I'm going to go to vars, y vars function to get my y1, and minus y vars function to get my y2. Then I'm going to close the parentheses and square. That's all inside the parentheses we're integrating. And then put my variable of integration x in the calculator. And that's going to give me 0.571 or 0.570. Remember, you can round if you round it correctly to 3 decimals, or you can chop. So this is going to be 0.57, I'm going to put O units squared. If you rounded it, it would have gone to 571. Units cubed, sorry. Units cubed because we're doing volume. And that's how we do with rectangular cross sections. In this case, the rectangle was twice as tall as it was long. Let's do one that is perpendicular to the y-axis as we review this. This time, let's look at the function f of x equals e to the x. Same process, except for this time, we're going to invert the axes so that we're integrating with respect to y. So, because this is perpendicular to y-axis. We're going to determine the volume of the solid whose base is defined by the region in the first quadrant, bounded by the curves f of x, y equals 5, and the y-axis. Again, I'm going to start by sketching this. I'll sketch it just like it's graphed with my normal x and y. So the curve f of x equals e to the x, recall, looks like that. The line y equals 5, be a horizontal line here. And so we're looking for solid in this region perpendicular to the y-axis with cross sections that are square. Now, because it's easier for me to see when I'm integrating with respect to the horizontal axis, I'm going to flip this entire thing. And when I flip it, I'm going to solve the equation for x. If I want to solve this for x, I let y equal e to the x. I take the ln of both sides, and that's going to give me ln y equals x. And basically what I've done is just turned my y value into my independent variable and my x value to my dependent variable. And if I graph the curve x equals ln y, and sorry, oops, draw. I get this curve. And if I graph the curve y equals 5, I get this curve. But now I can draw one rectangle perpendicular to the y-axis, and it's really easy to see how to integrate with respect to y. This, of course, if I plugged in 1 for y, ln1 is 0, so this is the value 1. So I'm going to be integrating a function from 1 to 5 to get this the volume of this cross section. Let's keep going though. Let's draw one of our cross sections. The width of the rectangle is dy. The length of it now is ln y. And this one's a square cross section. So its length and width are going to be the same. So it's going to be its length and height are going to be the same. So it's going to be ln y by ln y. So now we're going to write the expression for volume of one cross section. And that's going to be the length times height times width, or ln y times ln y. Let's go ahead and do squared times dy. That's the volume for one cross section. We, again, are integrating from 1 to 5. So we're going to integrate ln y squared dy. If you had to just set up the integral and not evaluate, that's exactly what you would do. If we're going to integrate this in a calculator, remember the calculator won't understand y as a variable, so we are going to instead change that y to x when we integrate the calculator. So this is just for entering in the calculator. This is what you would write on your FRQ response. But what we're going to write in a calculator is 0 to 5. Remember, we're going to open a new set of parentheses, do ln y squared, close a new set of parentheses. Then it's going to have another set of parentheses. That's everything we're integrating inside. And then, oops, sorry, I told you we're going to change those to x's in a calculator. You would put your answer here with what you did without the calculator in your FRQ if you had to do this. So here we go again. I'm going to, this one's just straight up integrate Math 9 from 0 to 5. Now we're going to open a set of parentheses because we're squaring what's inside. So I'm going to do ln x, close parentheses, squared. Oops, close parentheses again, squared. So now I have the ln x squared, and then integrate with respect to x in the calculator. And that's going to give me the volume of this solid is, it's still figuring, it's still figuring, it's still figuring. It might be hung up. Oh, no, there it is. 6.857. And this is going to be units cubed. And that's a review of how we integrate with, or how we calculate volume of squares and rectangles perpendicular to the x or the y axis.